Hello all, welcome to SSCA webinar series. Now our speaker is Rahul Shukla and his paper on stress strength reliability analysis of power function and Nakagami distributions using comparative sampling is being accepted in our journal Statistics and Application for publication, and it is being scheduled for publication for the forthcoming issue in June in volume number 24, issue number 1. Congratulations, Rahul. And without any further delay, please start your presentation. You have 10 minutes, so go ahead.
So, good evening, everyone. Myself, Rahul Shukla. I'm a research scholar at Department of Statistics, Baba Saheb Bhimrao Medical University, which is a central university situated at Lucknow. The title of my research article is, as such, already told, that stress strength reliability analysis of power function and Nakagami distribution using comparative sampling. Now, the core idea behind this research article is the stress strength reliability model, which is widely used in the reliability engineering field. It is defined by the sometime P, or in some research article, it is also denoted by capital R. So it is the probability of Y is greater than X. And here is Y. What is Y and X? Here Y is the our strength variable, and X is our stress variable. Both are taken as the random variables in the practical situations, in any systems or mechanical machines. The stress and stress both are moving randomly, so taking them as random variable is very obvious. And if a system works or not works, it totally depend on both variables X and Y. As we see here, a system survives when the strength of the system is always greater than the applicable stress. If the stress become bigger bigger than the our strength, which is fixed, then the system will fail eventually. And here the second component, or we can second model, is also we study here, which is the disaster probability, which is nothing but comes from the stress and reliability. Here it is denoted by the alpha, which is the probability of X is greater than theta, where theta is the threshold value, or you can set the upper bound of the strength. Uh, as we know that in the practical life, every systems have a, or you can say, if you take the example of a light bulbs have also a threshold value. For example, the voltage range. There is also a minimum voltage and a maximum voltage range. So it is defined as the threshold here, which is denoted by theta. Here we take two distribution. One is for the our stress variable, and second is for our strength variable. For stress variable, here I take the Nakagami distribution, and for strength variable, I take the power function distribution. The reason behind taking these two distribution is that for the power function distribution is taken for the strength variable is due to its limit, because the idea behind our research article is that we're fixing the upper bound of our strength, because in practical life and real life situations, the strength is always finite. We know that our system survive maximum load on which conditions. And as we see the PDF of the power function distribution, which is denoted by G, Y, mu theta. Mu theta are the parameter of this distribution. The Y variable, here the upper bound of Y variable is theta. So it is fixing the upper bound for this distribution, and we use this property in our stress and reliability model. And taking the Nakagami distribution is very obvious. And because when we study the literature, we found that stress strength reliability models uses generalized Wilbur distribution, Reddit distribution, and the very common distributions. But very few authors take the Nakagami distribution because it is a complex model. Because as we see the PDF of this distribution, it has two parameters which are denoted by xi and psi, and the PDF is complex, so the calculation become very complex if we go further in the advanced mathematics. So here we take this distribution so that we can drive uh, some new things. Uh, Next, here I suppose that the audience have already have my research paper, because this video will be posted on the research article. So I presented very crisp and clear information, not showing the full tables or full text data. So if it in my research paper there is a table which is a table 1. If you see the table 1, here I calculated the disaster probability, numerical the formula of the disaster probability which I derived for this situation is alpha, denoted by here alpha is equal to 1 upon under root xi, and in upper incomplete gamma function it is xi comma psi upon beta. Here beta is combined by two parameters, one of the parameter of power function which is theta, and one of the parameter of the Nakagami distribution psi. If we see the table 1 and first column, for xi, fixing the xi is equal to 0.6, we see that as the beta values increases, our disaster probability decreases. So this finding will be helpful for modeling our mechanical system. If we fixing the one parameter and want to know in which situation or which conditions our system will survive, and if this situation our system will fail, this table will help us a lot. This is the graphical representation of the table 1, which is represented already in my research article. Here the colors show the critical situation. As we see that as at beta is equal to 2.0, the probability is of failure is 0.98, which in percentage showing in 98.5. Uh, and as we lowering the beta values, so for example, if we take the beta values equal to zero point 0.1 for our model, uh, the probability of failure will decrease drastically, and which is come only 1 point, all comes to only 0.015 probability, which is denoted here in percentage. And second thing which we derived in our research article is the stress strength reliability. The numerical expression which we derived after taking the strength variable as power function is stress variable acts as Nakagami variable. It comes as probability P is equal to P is the stress strength reliability model. It is 1 upon gamma psi, and then the it is the incomplete and upper incomplete gamma in the form of functions. And uh, if we see if we see the next table of table 3, which is represented in our research article, here we calculate the reliability stress and reliability P for different combinations of the parameter, by fixing one parameter xi is equal to 2 point, xi at 2.5. Here fixing the xi at everywhere is making the whole article in a sequence, so that the reader will conclude that after fixing one parameter, what is the effect comes from the other two parameters, and it will help them in modeling and modeling their uh, machines, or further things, further research will be carried on based on this. As we see that as for beta, for lower beta values and higher mu values, the reliability is almost sure. Which is one. It is represented in the form of probability. So we can say that in these combination, the green cells show that the higher probability side, and as we say the red shows the lower probability, which is the failure. So there are few insights from this table. We see that what drives QE. what is the effect of the different parameters on stress tolerability. If mu increases, the reliability P increases, and if beta increases, the probability P decreases, and if beta tends to zero, it's almost the sure that our system will not fail eventually. And if beta is infinite, it is the stress overcomes the strength, and our system will eventually fail. Here we also combine two here we also compare two sampling schemes, which is one of the simple random sampling, and the second one is rank set sampling. Here this illustration shows us the how sample are done from the simple random sampling and rank set sampling. It is very basic things that how a simple random sample selected. As you said that if you select the sample
Rahul,
simple. Yes, sir.
yeah, I would request in another couple of minutes, can you please wrap up your
Okay, sir, sure.
sure,
Uh,
thank you.
this is a simple illustrations of the how rank set sampling, a simple random sample, and a sampling the sample selected. Uh, this is the findings of the we here use the maximum likelihood estimation for under the both sampling scheme, simple random sampling and ranked sampling, and these are the derivation which shows as the theorems in our research article. From theorem 3 and 5, uh, we uh, uh, we shows that the maximum likelihood estimations for the Nakagami distributions for parameters xi and for parameter psi and the combined parameter beta, which we combined from xi and theta of power function and Nakagami distribution. And theorem 4 gives us the maximum likelihood estimation for the parameter of power function distribution of parameter theta and mu. Eventually, by using the invariance property, we drives the maximum likelihood estimation for the reliability P. This is for using the maximum likelihood estimation under RSS, we use the Newton-Raphson's method by the R software, and uh, because all the four long likelihood equations come in the not in the closed form, so we cannot solve them numerically. So here we use the software for calculating the maximum likelihood estimations for the four parameters, and eventually we get the stress reliability peak for RSS. Within the simulation, in simulations, we find that the every time the relative efficiencies come greater than one, which denote that always the rank set sampling is model is performed better than the simple random sampling, and one times and the maximum relative efficiency we achieved in is 2.13. If we see the table of 5 of our research article, it is there. And in all the simulations combinations, almost in every cases, the mean square error is reduced by 50% as compared to simple random sampling. And we also here use a cost optimization. Here we take a
Rahul,
hypothetical
please
problem.
wrap up your
Okay,
present.
sir. Just a 2 minutes, sir. Just 2 minutes.
Please
Uh,
be.
Here we also use the cost optimization for taking a hypothetical problem, and we find that if we take the set size in the ranked sampling 3, it is the best results come from the ranked sampling, and the cost is optimized best in this case. So we suggest that the manufacturer to if they use ranked sampling, so they can uh, lowering the set size so that they get better results. And here are the some examples where we already use it in our research articles: turbine safety, elevated load limits, and electric components, where our models can be used and which is beneficial in the industry level. These are the some insights of research articles, and due to short time, I concluding now. So thank you, sir, for this opportunity.
Okay, thank you very much. Anybody have any question?